Hello, my name is Eva Med, and today I'll be discussing Lab 3, the magnetic field of a bar magnet. So in introduction, the purpose of this lab was to measure the distance of the magnetic field due to the small bar magnet by using our observations and data to determine the distance dependency relationship predicted by equations of on and off axis magnetic fields derived from our Biot-Savart law. So some key principles we want to start with was the Biot-Savart law, which we discussed in class, which computes our magnetic field, and the distance dependence relationship. So in terms of experimental setup, we wanted to first download the magnetometer app to find the net magnetic force, as well as the X, Y, and Z components. So we first located the magnetometer chip on our phone by orienting the phone. Note that we wanted to compensate for magnetic north by ensuring that B net was only a few microteslas within 49 microteslas, which is determined from our latitude and longitude of our location on Earth. And we also wanted to make sure that we compensated for the fact that the only magnetic force is the Earth's magnetic field. So here's kind of our experimental procedure for part 1, which is focusing on data collection for the distance dependence relationship. We want to orient the phone to find some X, Y, and Z components, but correct the Y component to make sure that the net magnetic field accounted for Earth's magnetic field, and repeat this procedure a few times to find 3 different values. In addition, we wanted to find a distance from the magnetized sensor to produce these BX components, which ends up giving us 5 different values for this part of the lab. The second part of this lab focused on data collection for measuring off-axis magnetic fields. We began with finding dperp and recording the Y component of the magnetic field, then added another meter stick to perpendicular to the first, and moved the phone along the second ruler to find X, Y, and Z components of the magnetic field. So before we go into our data, I wanted to go over some observations that I noted while I was completing this experiment. First of all, I observed an inverse relationship between the distance and the magnitude of the magnetic field. When the magnetometer was far away from the magnet, the F component of our magnetic field was close to 0, but as I moved the magnetometer closer, the magnetic field increased in magnitude. So here is my data for part 1, which was for the distance dependency relationship. As you can see here, as I increase the distance between the magnetometer, and I would see a decrease in the average magnitude of the magnetic field. But to kind of validate this, we wanted to plot the logarithm of both of these values to linearize this. So we would take the log of both sides, as you can see here, and get this equation, and then plotted this equation from the values there to kind of depict and illustrate how we could see an inverse relationship. The values of our line were then used to create some calculations so that we could find the magnitude of the magnetic moment, which was depicted by mu. So by using the slope and y-intercept, we were able to get mu is equal to 4.035 amperes. So part 2 data, we would use the values from the magnetometer app to find the magnetic field value or a vector and measuring it. As you can see here, these are the values that were gotten from the spreadsheet by plugging in our values from the magnetometer app, and we were also able to find the magnitude of our net magnetic force, net magnetic field. To kind of validate and also compare, I wanted to create a computational model. So we wanted to write up some code in order to find what would our how accurate the observed magnetic field was that we were able to calculate here. So we did this by first creating magnet, then we had to create the magnetic field, and then look at the field at different distances and observation locations and depict some arrows in order to illustrate this right here. So this was our final result from all the code in our computational model. The orange arrows depict our on-axis magnetic field, the blue represents our perpendicular, and the green represents the 45-degree angle magnetic fields. So we were able to then find a vector from the model and compare that to our experimental vector for the magnetic field. The model had the note that there were differences in the Z components, but the error could be attributed to procedural or experimental error. So here's some quick questions. What if you hadn't oriented your experiment to compensate for magnetic north and had instead laid your meter stick at some intermediate angle? How would the results have changed? We would note that the results would have been more inaccurate due to interference from other magnetic values from sources other than the bar magnet. In addition, what if you were to stick 2 identical magnets together end to end and run the experiment again? How would we expect our measurements to differ? The magnetic field would be probably stronger, and the distances measured between the magnetometer and the magnet would be smaller. So this concludes my explanation and presentation on Lab 3.